class? It's good to be with you again. We're going to be going over chapter 14 today, organic compounds of oxygen and sulfur. This is the first video lecture of a 2-lecture sequence in which we go over extremely important material because we're going to be discussing these groupings of atoms called functional groups. And FYI, these functional groups always find themselves on a Morris chemical concept exam. So make sure you know them. They're easy points if you just take the time and commit them to memory. Sometimes there is a lab that helps you go over these functional groups and to instill these concepts deep in your head. So without further ado, organic compounds of oxygen and sulfur, part 1. Today we're going to describe functional groups and explain why they're useful in the study of OChem. We're going to identify general structure of alcohols. We're going to identify features, structural features that classify them as primary, secondary, or tertiary. We're also going to be going over a number of functional groups today that I want you to commit to memory. We're going to name alcohols with IUPAC nomenclature and then explain why the boiling points of alcohols are higher than those of ethers and alkanes of similar molar masses. We're also going to explain why alcohols and ethers of 4 or fewer carbons tend to be soluble in water, while comparable alkanes are not, though we might not get to this discussion today because I plan on getting the ether lecture and the thiols next class, or the next video lecture. We're going to describe the structure and uses of some phenols. In next class, we're going to describe the structural differences between alcohols and ethers that affect physical characteristics and reactivities of each. And then we're going to describe the structure and uses of ethers, identify the structure of aldehydes and ketones, and finally finish up with thiols, also called mercaptans, which possess an SH group, a sulfur. Here's a quote by Sir Robert Boyle of the 1600s. God would not have made the universe as it is unless he wanted us to understand it. That is why we Christians do science. We see the beautiful work in the hand of the Creator God, who did all this to make the natural world around us to be studied and to be enjoyed. Hope you enjoy this chapter. First, I'm just going to start off with functional groups, okay? So make sure to commit these to memory. I highly encourage flashcards, by the way. Here's one side of the flashcard, and you're going to draw something like that. And then on the other side of the flashcard, you're going to put aldehyde. Okay. And so I highly suggest you do something like that for every one of these functional groups coming up. But before we get started on what the functional groups are, we need to know what a functional group is. It's a structural arrangement of atoms and or bonds that imparts a wide range of important properties to organic compounds. What this means is this. There's all kinds of chemical reactions and manipulations among molecules that can happen. And what occurs in organic chemistry is there are these groupings that we tend to see over and over again, a pattern of groupings of molecules. And each particular grouping, which you will learn the name of in just a second, has predictable chemical qualities, okay? I know that if I were to mix an alcohol with a strong base, it will get deprotonated. I know if I were to mix a ketone with a strong base, that base might act like a reacting agent at the carbon of the C double bond O. And so these groupings of molecules have predictable reactivity patterns so that we can know how to plan a synthesis of a more complicated molecule. These are very important slides coming up, so make sure you know the general structure of these functional groups as we discuss them now. So the first functional group we're going to talk about is one that you've already seen. This is the alkane and the alkene. And so the alkane is just a saturated hydrocarbon of just C's and H's. It doesn't really have a functional group name. It's just an alkane, and its suffix is ane. So butane, propane, pentane, heptane. Alkenes are a hydrocarbon with at least one or more C-C double bond, represented like that. And they typically have a suffix of -ene. And so we've already been through that in the last lecture. Y'all know what alkynes are. They are hydrocarbons bearing a C-C triple bond. There you have it. Their suffix is -ine. And now we're going to get into some new functional groups you have yet to see. And so first we have the alcohol, thiol, and ether. alcohol is ROH. I'll explain what this notation means. A thiol is RSH, and an ether is ROR. There's no clever way to memorize these. You're just going to have to commit these to memory, but I'll do my best. Notice that an alcohol and a thiol are the exact same structure, except the alcohol bears an O and the thiol bears an S, but otherwise they're the exact same, OH or SH. And the ether looks a lot like the alcohol being ROH, the ether being ROR. So the difference between an alcohol is you replace that H of the alcohol with another R group on the ether. Okay, I'll talk about what the R group is, so just hang tight. The the suffix of an alcohol will be -ol, and you probably knew that, whether you knew that you knew it or not, such as ethanol or isopropyl alcohol. You notice that these names end with -ol, so it works the same way. If you have 6, it would be called hexanol. If you had 10, it would be called decanol. If you had 7, it would be heptanol. If you had 1, it would be methanol. For thiols, it ends with thiol, and so methane thiol, ethane thiol, so on and so forth. And ether tends to end with ether, such as diethyl ether, methyl ethyl ether. And so that would be the suffixes you would be associated with. But what is this little R group we have going on here? Look at a periodic table. You will not find an atomic symbol that is just an R. This is one of the hardest things to explain in the entire chemical concept series. So just hang with me, see if you can understand what I'm trying to say. An R group is nothing more than an alkane of any chain length of any structure. Okay, it's an alkane or a hydrocarbon of any chain length or any structure, because carbon can be put together in so many different ways. And what we're trying to suggest with an alcohol is that it doesn't matter what's attached right here. It's just a random alkane. So we can just call this, my circle's not complete. We can just group that to just be R. Okay, it's just saying any alkane of any length attached to an OH is called an alcohol. So let me show you what that can look like. It doesn't even have to be an alkane. Let's just call it a hydrocarbon. So if that is an alcohol, then that means that's an alcohol. And that would be the R group. It means that that could be an alcohol, where that is the R group that I just circled. It means that I can draw literally anything. But if I put an OH, I'm saying that all of that is the R group. Okay, does that make sense? All what an R group is it saves you time from having to draw every single organic structure that could possibly fit there, which would take you years to do, and just say, hey, look, an alcohol is a functional group where an OH is attached to some sort of hydrocarbon. That hydrocarbon's identity is not important. Okay, it just has to be attached to a hydrocarbon. You're going to see this R group notation used time and time again whenever you're dealing with compounds that are not alkenes, alkynes, or alkanes. And so this also works for ethers. That's an ether because you have an R group on that side and an R group on that side, two alkanes or hydrocarbons. This is also an ether, where you have an alkyne and an alkene attached to either side, but it doesn't matter because that's an R group and that's an R group. Okay, for thiols, that's a thiol, and that is your R group. So just using the R notation saves you a lot of time and a lot of headache of having to draw every single possible carbon structure that could fit there, and just say, hey, it's any sort of alkane, alkyne, or alkene, a hydrocarbon of any sort. Okay, I hope that makes sense. It's the best job I can do at explaining this stuff. The next functional group is the aldehyde, which you're going to see as an R group attached to a C double bond O bound to an H. R, C double bond O, and an H. Now, I do want to point this out. In the aldehyde alone, you do have to emphasize that hydrogen, even though it is bound to a carbon. Okay, I know I told you in the alkane, alkene, alkyne sequence that the H's that are attached to carbons and line angle formulas do not have to be shown, but because this H is part of the actual functional group, it's best to show it on the aldehyde, okay? So I don't really like seeing this. I know that there's an assumed H right there to make carbon have 4 bonds, but go ahead and draw that H in because it emphasizes that you're showing an aldehyde functional group, okay? And so here's an example of an aldehyde, noticing that that is your R group. By the way, aldehydes end with Al, and so this compound that I just showed would be called, let me see, that's 5, so it would be called pentanal, and end with Al. Next up is the ketone. It looks just like an aldehyde, except for where that was an H with an aldehyde, now you have an R group. And so here's a compound you know and love that's called acetone. Okay, that's a 3-carbon ketone. But ketones just have R groups, okay? So that would be an R group right there, and that would be an R group right there. Ketones tend to end with one, O-N-E, such as acetone or propanone, or you can have like pentanone, so on and so forth. Now we have the carboxylic acid. It looks just like the aldehyde, except for the aldehyde was R, that. So the carboxylic acid has an extra O shoved in right there. Oftentimes students get confused and want to call this an alcohol because remember an alcohol was ROH. But remember, this R is a hydrocarbon. This is not a hydrocarbon. That's what we call a carbonyl group. Okay, that's a C double bond O. So a carboxylic acid has to have those chemical constituents right there, a C double bond O attached to an OH. Okay, so it's not an alcohol. It's called a carboxylic acid. If ever you've been bitten by an ant, you've found it at carboxylic acid because that's a molecule known as formic acid. And also if ever you've eaten a pickle or smelled vinegar, the active component that makes it so sour or makes it have that particular odor is acetic acid, which is this molecule, acetic acid. And so those are carboxylic acids. Do not get those confused with alcohols. Alcohol would look like that, so notice it doesn't have the carbonyl group right there, the C double bond O. And it's not a ketone because a ketone would look like that with no OH group right there. And it's not an aldehyde because an aldehyde would have had just an H there, but remember carboxylic acids have an OH. They end with oic acid. Okay, so that's the IUPAC name at least. You heard me rattle off formic acid and acetic acid. Those are common names. The actual IUPAC nomenclature would render it oic acid, like pentanoic acid. Okay, on this slide I want you to practice identifying what kind of functional groups are present in each of the following molecules. We're going to exclude using the term alkane because all these have so many functional groups all over the place. Well, I guess the bottom left one is an alkane, but let's go ahead and give it a shot. I think on the posted slides I gave you the answers, but let's quickly go through these right now. So take time and give it a shot right now before I go over the answers. You can hit pause if you must, and I will go over the answers now. So this first one right here, notice an OH, so that is an alcohol because it's not bound to a C double bond O. And right here we have an alkene, and that's all. And right here there's an R group bound to an SH, so that's going to be a thiol. Right here you have something that looks like this, which is a ketone. R, C double bond O, R. Right here you have another ketone, because you might notice that that's an R, and that's an R. It's just a hydrocarbon, so it still possesses this general notation, R, C double bond O, R. Right here you have something that is R and an R bound to an O, which makes that an ether. Ether. Some people call it ether. I like ether. Ether's fine. Right here you have a C double bond O attached to an H, and then an R group, which looks like this. One of the trickiest things is for students to not take the bait in looking at that functional group, or looking at the group and saying, oh, that's an R group. What you need to get skilled at is recognizing that although that's a benzene ring right here, it's nothing more than an R group, okay? So if you can just convert that to R in your head and then boil it down to this general formula, you'd realize that that's an aldehyde. Now, of course, that benzene ring is full of double bonds, so that's going to have an alkene component to it as well. CC double bond. This cyclopentane is going to be an alkane. That's pretty easy. Y'all have gotten good at those. Right here you have this. So don't take the bait. That's not an alcohol because it's bound to this C double bond O, which makes it a carboxylic acid, where that is just your R group right here. And of course, right there you see an alkyne. And then lastly, we have another carboxylic acid and an alkene. So practice these, make flashcards and get skilled at this. I want you to be able to get through these really quick on a test. Let me know if you have any questions or if you find any tricks to memorizing these quickly. But just try not to get these confused in your head. I know a lot of them look familiar and sound familiar even. Alcohols look like carboxylic acids, and they kind of look like thiols, except for there's an S, and they kind of look like ethers, except for there's not an H but an R. I get it. It's just going to take some practice, class. Let's take a deeper look at what alcohols are, one of the functional groups I just presented to you in this slideshow already. Okay, so an alcohol is an organic compound with an OH functional group on an aliphatic carbon atom, meaning it's attached to an R group or a hydrocarbon. Alcohols are represented by the general formula ROH. We've already discovered that, where R is an alkyl group, a hydrocarbon. Alcohols with 1 to 4 carbon atoms are frequently called by common names in which the name of the alkyl group is followed by the word alcohol. And you've seen this. The proper name for, say, this molecule, that's liquor alcohol, that's called ethanol. But you've probably heard people call it, so ethanol would be IUPAC. Like the standard naming, the formal way of naming it. The common name would be called ethyl alcohol. You probably heard that before, ethyl alcohol. So notice it only has 2 carbons, 1 and 2. So it has 1 to 4, so it's in that list. It's between 1 and 4. It's frequently called by the common names in which the name of the alkyl group, in this case that's an ethyl group, is followed by the word alcohol, ethyl alcohol. Of course, that would be called methyl alcohol. And this one, remember, that's an isopropyl group, looks like a V. So we oftentimes call that isopropyl alcohol, right? That's what your mom put on your cuts whenever you're a kid. It's a disinfectant. You will not be required to know the common names of alcohols for quizzes and exams, which means we're about to get into some IUPAC nomenclature. All right, class, I just wanted to give you this tidbit of information, more like an FYI in case you're wondering, well, why do they call it ethyl alcohol? Well, that's called a common name. It's different from an IUPAC name. Basic IUPAC rules for naming alcohols. You find that longest linear chain that contains the OH group, and that's taken as your parent compound chain. It's numbered from the end nearest to the OH group. The number that indicates the position of the OH group is prefixed to the name of the parent hydrocarbon chain, and then you take the hydrocarbon chain, such as pentane, you take off the E to make pentan, and then you add OL to make it like pentanol, hexanol, butanol, so on and so forth. And so let's do practice. Okay, so you may be tempted to number it from left to right. I advise you not to do that because that does not get you to the alcohol first. It does get you to these methyls first, but we're not going for the methyls now that there's an alcohol on here. We are going towards the alcohol portion, and you got to get to it first. So we're going to go 1, 2, because you can get to that alcohol at 2. If you numbered it the other way, you would have gotten to the alcohol at 4. And so here's our longest chain. You don't number through the alcohol, okay? There's going to be a carbon that bears an alcohol. And you may notice right here at 4, you have a 2,2-dimethyl. So we have 2, 2, oh, sorry, a 4,4-dimethyl, excuse me, 4, 4, dimethyl Now, where is that alcohol? It's on carbon 2, so that's what I got to indicate. 2, and there's 5 carbons, so pent and all. So that's how you do these types of problems. Let me give you one more example. I'm just making these up as I go. Let's do that one. I have no clue where this is going to take us, but one thing I know to start with is find that longest linear chain, and I know actually where to start the longest linear chain because I see where my alcohol is. So we're going to start here, 2, 3, 4. Now if you go down, you end at 5, 6. If you continue forward, you can get 5, 6, and 7. And so that gives you a heptane, or heptanol rather. Let me show you where my longest linear chain is. Keep in mind at carbon 6, I could have gone to any of those methyl groups and it would have given me the same name. All right, so what I see here is 2 methyl groups on carbon 6 and 2 methyl groups at carbon 5 and an ethyl group at carbon 4. And then my alcohol is at carbon 1. And so let's just add all this together. I know you might end up going a little bit slower than me. I have a lot more practice than y'all at doing this stuff. But we're going to alphabetize it. So ethyl beats methyl. Remember that the prefix does not count towards the alphabetical order. And so what we have here is 4-ethyl 5566-tetramethyl, because there are 4 methyls and tetra indicates 4, -1-heptanol. And so that's alphabetized because E beats M, right? There's only 1 ethyl, so you don't have to put monoethyl. It's just 4-ethyl. That tells me I have an ethyl right here at carbon 4. That tells me I have 5566, so there's 4 methyls, tetramethyl, 2 methyls on carbon 5, there they are, 2 methyls at carbon 6, there they are. And I have an alcohol at carbon 1 in a 7-membered chain. So don't worry about this rules 1 and 2. I took this from a previous slideshow. But here's a couple names. So see if you can derive the same exact name that they did. In this one, what it really looks like is that molecule. And so you might consider numbering it like this, which you'll see is there's 4, so that's going to give you a butanol. Your alcohol is here at carbon 2. And there's also a 2-methyl coming off of that chain right here. Okay, this one looks like this. So 1, 2, 3, 4, 5, 6. So that's going to be a hexanol. I'm going very fast, so make sure to slow this down. It's going to be a 1-hexanol because the alcohol is at carbon 1. You'll see it right here. And there's a methyl coming off of 3 and a methyl coming off of 5. So it's going to be a 3,5-dimethyl 1-hexanol. And lastly, we have a heptanol. And what do we have? We have 1, 2, 3. And a methyl coming off of here. So 1, 2, 3, 4, 5, 6, 7. Noticing that I met my alcohol at the nearest number, which is 3. I numbered my chain in such a way that I encountered the alcohol. And yeah, you'll see the alcohol there at 3, giving you a 3-heptanol. There's 7 carbons in my chain, and there is a methyl stemming off of carbon 6. Of note, I keep saying you have to number it in such a way where it includes the alcohol. Consider something like this. I can't even think of a case where that might not be the, yeah, something like that. You know that you could number this chain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But notice that chain doesn't even go through a position where you encounter the alcohol, so that won't work. Okay, it has to go through the alcohol chain. That's all what I'm trying to emphasize by saying that. All right, classification of alcohols. First up, we're going to talk about what a primary alcohol is. It's a compound with an OH group and a carbon atom that's attached to only one other carbon. A secondary alcohol is very similar, except for the carbon that it's attached to is also attached to two other carbons, and a tertiary has the alcohol portion, the OH, attached to a carbon attached to three other carbons. So let me show you how I figured this out. I'm just going to give you random examples. Okay, here's how I solved this. What I do first is I look for the carbon that the OH is attached to, and I put a dot on it, okay? So my red dot indicates the carbon that my alcohol is attached to. And then I ask myself, how many other carbons are attached to my red dot? How many carbons are attached to my red dot? Well, what you're going to find is there's 1 and 2, which means that that's secondary. What you're going to find in the second one is that there's only one other carbon attached to that red dot. That's going to make that primary. In the third example, there's 3 carbons attached to that dot, which makes that tertiary. In this cyclohexanol, there's only 2 carbons attached to my dot, which makes that secondary. And finally, there's only 1 carbon attached to this last example, which is a primary alcohol. And so I suggest you use that trick I do. You might want to bring a scratch paper on your next exam to make sure you can do this. But what I do is I locate the carbon that my alcohol is attached to. And then once I locate that carbon, I ask myself, on that carbon, how many other carbons is it attached to? And based on that number, it's going to tell you whether it's primary, secondary, or tertiary. Here's some classification and nomenclature of some alcohols. And so don't worry about common names. Like I said, I did bring that to your attention, but don't worry about common names. CH3OH has 1 carbon, so it's going to be called methanol. CH3CH2OH is going to be called ethanol. 3 is going to be called propanol. And what that one looks like is this. That one looks like is that. And that. Now, whenever you get here, this one's going to be called 2-propanol. The common name for that was isopropyl alcohol. Okay, there you have it. And then that's a secondary alcohol because it's attached to a carbon that's bonded to 2 other carbons. What you have here with the 4 sequence is butanol. And then there's also sec-butanol. Whoops. Which, where am I at? Yeah, sec-butanol, secondary butanol, and so on and so forth, okay? And then you have cyclohexanol with the cyclic hydrocarbon. And so I just wanted to show you that it works all the same way. So where you would have said like isopropyl alcohol, or sorry, where you might have said like propane or propene or propine or something like that, now you're going to say propanol. So these all kind of act the same. So in the next slide, let's determine if these are primary, secondary, or tertiary alcohols. Oh, of note, this one is. So that's a tertiary. All right, so to determine this, let's use that trick I showed you previously. So I'm going to draw a dot on the carbons that my alcohol is attached to. It's important that you're good at identifying this dot, okay? If you don't get your dot right, you might screw this one up. So just locate where the OH is attached to, put a dot there, and then find out how many carbons are attached. This first one is 3, so it's tertiary. This one under it is attached to 2, so it's going to be a secondary. The one under that is attached to 2 carbons. See that? A carbon here and a carbon there, so that's secondary. This one is only attached to 1 other carbon, so primary. This is attached to only 1 other carbon, primary. This one's attached to 2 carbons, so secondary. So don't get bogged down to look at what the actual species is. So if you go up to the bottom left right here, you may say, well, Dr. Morris, I get how this is a carbon right here, but this looks like it's attached to 3 carbons. No, don't fall for that trick. It's attached to only 1 carbon, and that carbon's attached to other things. But don't worry about what else that thing's attached to. Who cares? All what you're looking at is how many carbons is my red dot attached to, okay? So continuing on the upper right, my red dot is attached to a carbon right here, a carbon right here, and a carbon right here. So it's going to be tertiary. This particular alcohol, which bears a benzene ring at the middle right, it's only attached to 1 other carbon. You see that? That's all what you're concerned with. So that's primary. And lastly, you have a secondary alcohol because it's attached to 2 carbons. So hopefully that makes sense. You may want to practice. It doesn't come easy for many students. Now we're going to look at something a little tricky, I suppose. Alcohols can be considered as derivatives of water. Now, why in the world would I say that? Well, I want you to consider this. Water is HOH. Now, what happens if you replace that H with an R? Well, now you get an alcohol. Okay? And what happens if you replace that H with another R? You get an ether. So that's what we want to look at, okay? All these are just derivatives of water. So you're sequentially changing an H for an R group, which is nothing more than a hydrocarbon. Alcohols can be considered as derivatives of water, and like the HOH bond in water, the ROH bond is bent in terms of Vesper theory, molecular shape, and the alcohol molecules are thus polar. It's polar because oxygen is electronegative, so you can imagine a dipole moment existing like that. And it's also going to be hydrogen bonding as an intermolecular force, of course, along with dipole, and dispersion. But remember, H2NO or F equals H bonding, and that was your strongest intermolecular force or intermolecular interaction. That one, if you have that one, you can assure yourself you will have high boiling points and high melting points because it's a strong intermolecular force. And so you may notice that alcohols and water have hydrogen bonding because you have this H bound to an O, which fits this to that, okay? Which means it hydrogen bonds. They're also polar, right? Because it's bent and the dipole moments don't cancel. See, they can just go on forever without canceling each other out. Whereas like linear molecules, they do cancel out their dipole like a tug-of-war match that's at a standstill. Okay, alcohols have higher boiling points than do ethers and alkanes of similar molar masses because the OH group allows alcohol molecules to engage in, like I said, hydrogen bonding. Hydrogen bonding is a strong intermolecular force. Alcohols can engage in hydrogen bonding with water molecules, and they can also engage in hydrogen bonding with themselves. By the way, hydrocarbons are insoluble in water. Alcohols with 1 to 4 carbon atoms are completely soluble in water. As the length of the chain increases, the solubility of alcohols in water decreases. The molecules become more and more hydrocarbon-like and less water-like. Let me explain, because this is very confusing, I imagine. So, consider this. If you are water, and then you just replace that hydrogen with a CH3 to make methanol, it still possesses pretty good character of the OH group, which has hydrogen bonding, compared to the CH3, which possesses alkane-like qualities. And so what I want you to do is to imagine alcohols being like a mixture of like a water and an alkane. So you know water is going to be water soluble, obviously, and alkanes are not water soluble. So R, OH. And the question is, which one wins? Does the R group win in terms of solubility, or does the OH group win in terms of solubility? Well, as this slide tells you, if your carbon length is 4 or less, okay, so 1 to 4, they're going to be soluble in water, which means methanol, ethanol, propanol, or isopropyl alcohol, propanol, butanol, and the isomers of butanol. Those are all soluble in water. Why? Because if you were to cut this in half and say there's an alcohol portion and an alkane portion, it's kind of saying that this portion is winning, so it's going to be soluble in water. So that chain length is losing. This chain does not want to go into water, but I would say that the OH portion wins the battle. It's going to go into water because the strength of the OH is going to outweigh the length of the carbon chain. Now, whenever you exceed that 4 and you get to 5, now the alcohol starts to lose, and it's no longer soluble in water, but it will be soluble in organic solvents, okay? I hope that makes sense. Just think of it as like you finally tipped the scale to go to the other side, and now the hydrocarbon part of the alcohol is beating out the water-soluble part of the alcohol, so it will not go into water anymore once you get past 5 or more carbons, okay? So just think of it as like a little battle being waged and trying to find out which one is actually going to win the battle. Is it the alkane part or is it the OH part? The OH part wins until you exceed 4 carbons. So here's some intermolecular hydrogen bonding in methanol. All it's showing is this. And so let's say that there is another methanol molecule here. You see how they can hydrogen bond with themselves. So there's an OH, so H to NO or F. So they're hydrogen bonding with the other molecule's oxygen, and that's all this is showing with a cluster. Now we can compare some boiling points and molar masses of alcohols. And keep in mind, I don't want you to know the specific numbers, but to know the trend. And so if you were to take methane, which has a molar mass of 16, and water, which has a molar mass of 18, notice the difference in boiling points. Negative 164 to 100. Well, that's because water hydrogen bonds and methane doesn't. In fact, methane doesn't even have dipole-dipole. All what it has going for it is dispersion, and every molecule has that. And so, of course, it's going to get beaten by water in terms of boiling points. Now, let's compare ethane, which is just CH3, to a alcohol of similar size, methanol. Notice ethane is minus 89, whereas methanol is 65. This is because of H bonding. Okay, of course, ethane is nonpolar. Again, it's only going to have dispersion going for it. Methanol has hydrogen bonding. Propane and ethanol, similar molar masses. Notice propane, again, it's not polar. It's not going to have anything going for it. It does beat ethane because negative 89 to negative 42, and that's only because the chain length increased by 1 carbon. But when compared to ethanol, which does hydrogen bond, notice how different the boiling points are. So hydrogen bonding really increases boiling points. You see it again in this series where these two molecules have about the same molar mass. Butane versus propanol, hydrogen bonding completely beats molecules that don't have hydrogen bonding. So that's the trend we see. Alcohols have much higher boiling points than alkanes when comparing similar molar masses. I'd also mention that hydrogen bonding can occur between methanol, or alcohols rather, and other water molecules. So not only is methanol doing what I showed in the earlier slide, where there is hydrogen bonding between methanol molecules, but you can also have remember how I said like 1 to 4 carbons are soluble in water? Well, this can also exhibit hydrogen bonding as well. So let me show what that looks like. So you may notice that that oxygen is hydrogen bonding there, that's hydrogen bonding there, so on and so forth. So you have this little clustered network of hydrogen bonding amongst water molecules, and in this case, well, this is ethanol. That's misleading. That's ethanol. And so hydrogen bonding can occur between any 2 or 3 or 80 molecules that have H bonded to N or F. So they can hydrogen bond with each other in like a pure solution of methanol, or if you dissolve methanol in water, it's still going to have a high boiling point because it can also hydrogen bond with water as well. Glycols and glycerol. A glycol is an alcohol with two OH functional groups, such as this. So you might have heard of ethylene glycol. Ethylene glycol is this molecule. Notice that right there and right there you have an alcohol attached. Actually, that's propylene glycol, excuse me. That would be ethylene glycol right there, where you have two carbons. Commonly called glycerol or glycerin, 1,2,3-propane-triol is the most important trihydroxy alcohol. We're gonna talk more about this. Glycerol is the product of hydrolysis of fats and oils. So what this is so that's a triol, 3 alcohols. So that's 1,2,3-propane-triol. It's the most important trihydroxy alcohol. Keep in mind that these groups, though that's an alcohol functional group, that particular substituent is called a hydroxyl group or hydroxy group. Just like methane is CH4, but when CH3 is attached to a longer chain, it's called a methyl group. That's similar to what's going on here. OH is called a hydroxyl group when it's listed as part of the longest chain. And glycerol is the product of hydrolysis of fats and oils. I had previously mentioned that. It's a sweet, syrupy liquid, and that's the structure right here. Some people draw it like this. Sorry. Okay. It's the same thing as what I drew here. And phenols are aromatic compounds with an OH directly attached to a benzene ring. So that's phenol right there. The parent compound, C6H5OH, is itself called phenol. It's a white crystalline compound that has a distinct odor. And so all what I'm saying is phenols are any compound that might have, all kinds of things attached to it. But the actual compound itself, C6H5OH, is called phenol. You will want to know that. It's the one I talked about that is in throat sprays for that numbing property, and it's also highly dangerous in the industrial sense. There's the structure right there, used as antiseptics and disinfectants. So sorry this is a longer lecture. Hope you kept up. I'm going to be giving you part 2 of this lecture coming up soon. Have a great day.